Okay, now let's talk about how to calculate the confidence interval for variance of a standard deviation. And this will be an interesting case because in this case we don't have a symmetrical distribution. So let's talk a little bit. First of all, let me remind you of variance. The variance, it's one of the parameters of normal distribution that tells you how far your values can go from the average value, from the center, right? And this is how to calculate variance for the population. Is just an average squared distance from all your values to the average. This should be mu, of course. Okay, and this is mu as well. And then standard deviation is just a square root of the variance. Okay, but for the sample we calculate it using n-1. You remember that we lose 1 degree of freedom when we reuse the same values for calculating both average and standard deviation, or variance in this case. Okay, so let's talk about this. First of all, the variance itself doesn't follow any distribution. However, we have a distribution, theoretical distribution, that describes very well a sum of squared values. Okay, this distribution is called chi-square distribution, and that's how it looks like. So this is a chi-square distribution, and this is chi-square statistics. This is density. This is density. And it depends only on one thing. It's the degrees of freedom, because chi-square distribution describes behavior of sum of squared values taken from normally distributed population and standardized. So it means that the standard deviation is 1 and the average is 0. So what it means? For example, this is our normal distribution. So this is x values, right? Or we can call it z values. The standard deviation is 0, so mu is 0. And sigma is 1, standard deviation is 1. Let's take, for example, 5 values here. So it will be something like this, like this, like this, like this, and like this, okay? So we have 1 here, 2 here, -1 and -2, okay? So you can see that, for example, we've got, let me just get some values. We've got -2, then we've got -1, then 0, then 1 and 2. So these are our random values from this standardized normal distributed populations. So if we take a squares, so if we square the value, we have 4 here, 1, 0, 1, and 4, and then take a sum of the squared values, we will get 10, okay? And this is our statistic. So statistic for this particular case is 10, okay? Is it extreme or not? Well, we have the red line, this one, for 4 degrees of freedom, sample size 5, and then you can see that actually this chi-square statistic can go somewhere between 0 and maybe 18. So the 10 is somewhere here, so it's pretty, not very, you can see that this is the peak, this is the most dense value, right? It's somewhere around maybe 5, but 10 is also okay, 10 is also okay. Then let's say we repeated this, this experiment, and we've got, for example, 2 times -2, -1, 1, 0, and then 2 times 1, like this, okay? So in this case we have -1, -1, 0, 1, 1. The squared values will be 1s, and then the sum will be 4, right? And then you can see that 4 is somewhere here. So it's pretty okay. Okay, so that's it. So it tells you a distribution. So if you take n random values from normally distributed population, from standardized normally distributed population, then take a squares, let me use x squared, take a sum of squares, these values. Then the sum of square will depend, of course it will be a random number. Every time you take a new sample, you will have different numbers, right? But the sum of square of these numbers will be distributed somewhere in between, okay? And the shape of the distribution, it depends only on degrees of freedom, okay? So how can we use this for our calculations for the variance? Well, let me show you this one. So in this case, we have a sample size 10, and this is the chi-square distribution, okay? If you take, for example, 95% of most common values, it will look like this, something like this, I think. Okay, then this will be 2.7, and this will be around 19. Okay, so it means that if you take 10 random values from normally distributed population with standard deviation 1 and average 0, then the sum of squares of these values will be somewhere, in most of the time, 95% of the cases, it will be somewhere in between, okay? So how can we use it for getting confidence interval for the variance? Well, first of all, what if our x values, they are not standardized, right? They are non-standardized. They have their own standard deviation and the average, right? So how we can standardize them? Well, we know there is an operation which is called standardization, which will be x minus mu x divided to sigma x, right? So this is standardized values. But because we don't know mu, we will use simply the sample m, because it gives us a very good idea of the center of the values, right? Now we don't care about the center, we do care only about the spread. So it will be x minus mx divided to sigma, right? Then this chi-square statistic, sometimes it's called chi-square, sometimes it's called chi-square. Actually, the correct pronunciation is chi-square, but many people use it as say it as a chi-square. So the chi-square statistic is a sum of these squares, okay? So we can just take a sum. So it will be a sum of x minus mx divided to sigma squared, or it's a sum of x minus mx squared divided to sigma squared, okay? Now look at the denominator, this part. This is exactly s squared, but without n minus 1, right? So you remember that the variance for the sample, it's this one. It's x minus mx squared divided to n minus 1, right? So it means that we can rewrite it like this. It's s squared times n minus 1 over sigma squared, okay? So that's the chi-squared. And every time we take a new sample, the s will be slightly different from sigma, sometimes not slightly. But the variation, the ratio between s squared and sigma squared, is defined by this distribution. So this distribution tells you sort of how big can the variance of your sample differ from the variance of your population, okay? But on the other hand, if you know that, for example, if you know that it can be 2.7 and 19, right? So you can switch this. So instead of, let me write it again, chi-squared equal to s squared n minus 1 over sigma squared, right? So you can write it like this. You can write the sigma squared equal to s squared n minus 1 over the chi-squared, okay? So if we take the smallest possible value, for example 2.7, well, we get the largest possible variance for the population. And if we take the, for example, 19, we will get the smallest possible values for population. So that's how to get the confidence intervals. That's how to calculate the confidence interval, okay? So once again, the intuition is very simple. Because chi-square distribution describes the sum of squared values of random sample taken from normally distributed population, we just take standardized values for our sample and then use simply sum of standardized squared values to get this relationship between the chi-square statistic, between the sample variance and the population variance. And now we can use, if we know the chi-squared values, like we calculated t value, for example, or z value for normal distribution, we can calculate these chi-square values for any given probability, And therefore we can just simply calculate the confidence intervals for the variance of population. Okay, so the idea is the same once again. For example, when we calculate confidence interval for the average, for mu, for population average, we just decide the confidence level, so how many values, most common values, for example 95%, we need in between. Then we found either this z value for the left tail and z value for the right tail, or it can be t, okay, it can be t. But in this case, because the distribution is symmetric, we found only one value and then just take a minus, okay. In this case, we have to find two values, this one. So this will be the chi-square for n minus 1 degrees of freedom and, for example, 0.975 for 95%. And this will be chi-square for n minus 1 degrees of freedom and 0.025. Why? Because we have 2.5% here. And then if you take this one and what is on the left, it will be 97.5%. Okay. So and as soon as we know these two values, we can use the formula we just derived together for calculating confidence interval. So that's the final solution here. This little alpha, let me explain that. you remember that we have a confidence level, for example, confidence level 95%. Okay. Alpha is called significance level. It's a sort of opposite to confidence level, and it's expressed not in percent but in ratio of 1. So alpha, it's always 1 minus confidence level divided to 100. For example, for this particular case, for 95% confidence, alpha will be 0.05. It's 5% values you have on the tails, right? And then you have left tail and right tail. How? So the left tail, it's alpha half, 0.025. And the right tail is your 1 minus alpha half. So for 95% confidence, it will be 0.975. Okay, so these are the meanings of these alpha values. You just calculate the chi-squared for a particular probability.